we want to find out what special relativity is, and this fellow comes along. He says the following. He says that time dilation, right, has been proven. He says, breaking news, just in. He shouts it, right? That's what happens with all these people. AI rediscovers Einstein's time dilation. Okay, how an AI, artificial intelligence, right? It's got a little robot there that rediscovers Einstein's time dilation. Okay, I'm not sure how an AI can do that, especially when AIs are actually programmed. But let's see where this leads. What is special relativity? Well, special relativity has three essential theories built into it. One is that mass increases at a given speed when it speeds up, right? Rulers, lengths of rulers, right? They contract when an object speeds up, and time dilates. Okay, so they have these three versions, and here I've illustrated them for you. Okay, a ruler contracts in the direction of travel, right? Mass increases. And I guess like a balloon, you just inflate it, or are there more atoms? I don't know. And then time dilates. Okay, somehow the clocks become wobbly, Okay, these are the things that special relativity has, and therefore you can see that it's all going to be a bunch of nonsense, what they're going to be proposing. Okay, so this is not for you to take seriously, this theory of special relativity. Okay. Where did we get all this stuff? Well, we have a little summary here from one of our primary physics sites, Physics World, right? It says length contraction, the short story. Okay, the idea of length contraction was postulated by the Irish theoretical physicist George Fitzgerald in 1889 and by the Dutch theorist Hendrik Lorentz in 1892, also known as Lorentz-Fitzgerald contraction, or just Lorentz contraction. They forgot about Fitzgerald, right? It was invoked to account for the negative outcome of Albert Michelson and Edward Morley's memorable experiment of 1887. The two Americans had famously tried and failed to detect the ether, a hypothetical stationary medium that was supposed to carry electromagnetic waves, much as the surface of water carries water waves, right? Keen to rescue the hypothesis of a stationary ether, Lorentz and Fitzgerald's solution to Michelson and Morley's null result was to suggest that objects traveling at a substantial fraction of the speed of light will, when viewed by another observer, meaning subjective, right, appear shortened in the direction of their travel, based on a calculation by Oliver Heaviside of how the magnetic vector potential in Maxwell's equation transformed between reference frames. Okay, so what does this history look like? Let's go slowly, point by point. What happened was that we had first these two fellows, Michelson and Morley, and they carried out a series of experiments. The last one was in 1887, up to that point. I think they had a couple more after that, but the main one where they published their main result was 1887. Okay, think about that. 1887, Einstein was from 1879. He was 8 years old. Okay, keep this in mind. Okay, Einstein was only 8 years old. Did he discover any of this stuff that we're going to look at in a minute? I doubt it. Okay, not at the age of 8. Okay, so here it is. This is Albert Michelson and Morley. And what they did, they said, look, if you put some kind of sensitive device when the Earth is on one side of the sun and when it's on the other, they should be going in opposite direction to the ether wind. Okay, and so they carried out this experiment in which they sent beams of light. Okay, and you can see there on the right what happened. They showed that what should have happened and what did not happen. And essentially, they came up and they said, look, by the way, we conclude that there is no ether. They thought there was an ether, a bunch of particles, as I call them, out there in space that would slow down light. And that did not happen. Light had the same speed in any direction. They could not detect any difference. And because of that, they got rid of the ether. And a lot of people didn't like that because everybody up to that time had been nurtured in high school and college that there was this ether out there. So everybody just took it for granted. Yeah, there is an ether. We've had the ether all the days, every year since the days of the Greeks. So, it was like, you're not going to take that away from me now, are you? I mean, Newton said there's ether. Huygens said it's ether. Even Descartes and Galileo, all of them said there's ether. Now you're telling us that there is no ether? So Michelson and Morley's experiment was, in that sense, an eye-opener. People started complaining about the fact that something must be wrong. Maybe the measurement is wrong, but if the measurement is right, then perhaps there's something else that we don't understand. And that's when some of these people came up with alternative ideas. And the first guy to attack that to some degree, okay, was Oliver Heaviside. But he did not really attack the Michelson-Morley experiment. What he did, he went in there and he was talking about charges that move. And he figured out something that when they move in the direction in which they're traveling, when they move in that direction, he said that there's something going on with them flattening out. The charge is flattened out. So he puts this paper, and what I like about this paper, he says the following. He says, all disturbances being propagated through the dielectric ether at the speed of light, when therefore a charge is in motion through the medium, the discussion of the effects produced naturally involves the consideration of three cases. Those in which the speed u of the charge is less than or equal to or greater than v, that of light. So you can see there I circled in his equation 1 minus u, which is the velocity of the charge, over v squared, which is the velocity of light. And the reason I put that in there, that's the first time I saw this relation, okay? And what I'm saying is that's what Lorentz is later on going to incorporate into the so-called Lorentz factor, which then, in the end, Einstein takes credit for all of it. Okay, but you can see this is coming in out in 1888, at the end of 1888, beginning of 1889. That's when he published a series of 5 papers. And this was from the 3rd or 4th, which was still 1888, the end of 1888, November, December. And you can see that that relation there, I think he's probably the first guy to put that in there. Okay, and that's going to be very important. Keep that one in mind, because you're going to see now what's going to happen. The next fellow to take that information, okay, and use it to say, well, we can explain maybe what happened with Michelson-Morley with that experiment. Maybe something is flattened out. Maybe light is being flattened out, okay? And so this is the article put out by Fitzgerald. It wasn't really an article. He just wrote a letter to Science Magazine in those days. And he says the following. He says the important part, right? He says the length of the material bodies changes according as they are moving through the ether or across it. Okay, so he was saying that something is happening to the length of the material body itself. Okay. Okay, so we already have the notion that something's happening to the objects. The objects are getting flattened out in the direction of travel. The first guy to notice that or to suggest that was Heaviside. Now comes 1 year later, or in that same year, really, because the 5th paper published by Heaviside was at the beginning of '89. Same year, Einstein is only 10 years old. Okay, same year, Fitzgerald just writes this note. He became famous for that note alone, just that little letter that he wrote. But first guy to take credit for stuff that he didn't do is Lorentz. He goes in there and he uses this factor called the Lorentz factor. And there you see the factor at the bottom right. 1 minus what? V squared, meaning the velocity of the object, over c squared, which is the velocity of light. So he takes that factor, he gets the square root of it, 1 over that, and he's going to use that factor to calculate length, contraction, right, mass, and time eventually. Okay, and this was the work of different mathematicians in those days, but Hendrik takes the credit at least for the Lorentz factor, which again, I think really the fellow who zeroed in on that first was Heaviside. Okay, and again, Lorentz publishes that in 1892. Einstein is what, 13 years old now. Okay, I don't think he knew about any of this stuff at the time. Okay, and what happens? Einstein comes in in 1905. Several years later, he's 26 years old, and that's when he gets the credit for relativity. He writes a paper on that in 1905. His first, I think it was his first or third paper. I can't remember now. Anyways, he publishes that, and he's going to get the credit for special relativity, which is disputed by Poincaré, French guy. Also, he said, "Hey, I did all this work on special relativity. This guy gets the credit." Okay, so they had that situation there, and again, Einstein said there was an ether, and they were fighting over the nature of the ether that Einstein proposed versus the one that Lorentz and Heaviside and all these other people proposed. These other people were proposing a static ether, so it was standing still and everything was moving through this sandbox. That was the way they saw it. And Einstein saw it more as a dynamic ether. Okay, and so petty stuff. There is no ether, so it doesn't matter one way or the other. They were all wrong. Okay, but those are some of the differences between them. Okay, let's look at this. First, the mass increase. Okay, they're saying that if an object travels close to the speed of light, because of the Lorentz factor there, that 1 minus v over c, both squared, right? That factor is going to tell them that the more you approach the velocity of light, the more you're going to be affecting mass, length, and time. Okay, and let's look at mass. This is what they're saying, because they're saying the effect is real. Okay, it's not an optical illusion. Okay, they're saying it's a real effect. Okay, and here it is. Okay, I'm going to illustrate it here. What they're saying is that an object that travels close to the speed of light, think of that as traveling close to the speed of light, expands. Okay, and so the question is, what happened there? Did more atoms? Did that object, that ball, acquire more atoms? Is that what happened to that object? And if so, by what mechanism? I mean, how does speed explain that the object there, this ball, acquires more mass? Mass being the quantity of matter. Okay, so that's the first problem that anyone would have to answer. But now let's superimpose on this the fact that there's going to be as well a flattening out of the object in the direction of travel, something called length contraction. Let's put them together, and this is what it looks like. Okay, you can see not only is it gaining in mass, but it's also, flattening out in the direction of travel. And the question is, again, by what mechanism is this happening? How is it that it acquires more mass and at the same time flattens out? If this is not an optical illusion, if this is real, So these are the questions that these folks need to answer. And of course, they don't do physics. They just want to do math. They just say, look, we put the Lorentz factor in there, and that's what we get. Yeah, great. And then they say, oh, we measured and we obviously proved it. Okay, so here we have the Internet Encyclopedia of Philosophy. And if these people don't know, nobody else knows. They say this effect is real. Okay, it says objects and processes are said to look shorter or longer when viewed in one inertial frame rather than in another. Okay, that means it's subjective. If it looks to you different, we don't care, because that means you just had more beers to drink. Okay, or maybe you shot up, who knows. It is common to regard this effect as a purely conventional choice of reference frame. But this is rather misleading, because time and space dilation are very real physical effects. Okay, that's what these people are saying. They say it's a peer-reviewed academic resource, right? There is no answer within special relativity as to which rod really gets shorter. We could consider these effects as a matter of perspective, although it is more accurate to say that in special relativity, in its usual interpretation, there are simply no facts about absolute length or absolute time or absolute simultaneity, okay, at all. However, this doesn't mean that time and space dilation are not real effects. So they keep chasing their tail around. They don't explain it, but they say, oh, they're for real. We've proven it. Okay, how can you prove that, for example, mass increases? I mean, what are you saying, that it acquired more atoms? Is that what you're saying? And then they say, well, when it comes back to rest, to your frame of reference where you're going to take the measurement, it went back to normal. So how do you prove, to anyone, to God, that this thing became bigger because it acquired more mass, more atoms, just by traveling at the speed of light? In fact, that would seem like they're talking about weight and not about mass. Mass is the quantity of matter. Weight is the effect of, say, the Earth on an object, how close or far away you are from an object, as far as mathematics is concerned, right? And so the issue here is this thing is going closer to the speed of light means you got to look at it as if it approaches something, and now like a scale, and it's going to press on the scale because it's traveling close to the speed of light. That's called weight. It's pressing down on the scale very strongly because it's traveling close to the speed of light. If on the other hand, it goes slow or is in your frame of reference, well, then it weighs whatever it weighs. It goes back to that. Suddenly it lost all those pounds. Just stop moving at the speed of light and you'll lose a lot of weight, A bunch of nonsense. Okay, so these are the questions that I have for all these special relativists, right? Mass, quantity of matter, or measure of quantity of matter, right? If mass is increased, the object acquired more atoms. Okay, that's what they're saying. Okay, by what physical process did the object acquire these extra atoms? That's all you have to answer. Just tell me the physical process. This is physics, right? So we don't care about your math. We don't care about the calculations. We don't care about any experiments you did. We just want to know the explanation. We want to understand the explanation. Tell us by what mechanism the object acquired more atoms, which is what mass is if they're going to talk about an increase in mass. In other words, they're just saying that it weighs more because it's pushing down at close to the speed of light rather than at a slow pace. So it's pushing on the scale at close to the speed of light. It's like if you jump on the scale, well, yeah, of course you're going to weigh a little more than if you just stand there. And that's the difference that they're talking about here. Motion versus standing still. Okay? So if they're not talking about weight, they're really talking about mass. They're talking about acquiring more atoms. Please tell us the mechanism. Length, what is length? Continuous matter lying between two surfaces. That's what length is. Okay? We don't measure length. We define length so that we don't have to measure. Okay? We don't know how long something is. We don't care. We want to know if it is long. And for that, we need a definition. The definition is you take a table, you treat it as if it were made of a single piece, and you look at surface to surface. That's called the length of that table. It's a qualitative concept. It's the one we use in physics. We have no use for the quantitative measurement notion that they have in math. If the object shrunk, it either lost atoms or the atoms came closer together, right? So if it shrinks, what happened? The atoms just came closer together for whatever reason, or you chopped some, or they lost some, or whatever, and that's why it also became shorter, right? Those are, I think, the only two possibilities. Maybe I missed one, okay? So, and again, so by what physical process did the object do either? That's what you got to answer. How come it became shorter? Okay, and again, we don't care about the math. We don't care about experiments. That's not what we're asking. We're asking for a physical interpretation. Time dilation, what is that? An observer measures a moving clock as ticking slower than a clock that is at rest in his reference frame. Okay, what does that have to do with physics? It just says that we have a subjective reading because the object, whatever it is, in this case, could be a clock or whatever, it ticks at a certain rate. It doesn't matter what you measure over here, what another guy measures over there, depending on their frames of reference. We don't care about that. We want to know what the clock itself reads. Hopefully the clock only has one reading. And I'll give you a good clock, the Earth going around the sun. It takes 1 year. 1 year is defined as one revolution of the Earth around the sun. So if one twin, right, we have two twins, one travels at the speed of light to the galaxies, to a black hole, and then comes back, and he says he's younger than his brother because time went slower for him, that his brother is 50 or 60 years old, he's only 20. Well, let's count the number of times the Earth went around the sun, and we'll find out who's right. And hopefully the Earth went around the sun 20 times or 40 times or 50 times. It can't be both. So we have to use the definition. What is a year? A year is one revolution of the Earth around the sun. And whether the guy comes out there and measures with his atomic clock and comes back and stands on his head, we don't care. We want to count the number of revolutions of the Earth around the sun, period. That's all we have to look at, okay? And so the way they got around this is by talking about proper mass, proper length, and proper time. What is that? Well, proper means what they measure in their local frame of reference. In other words, the thing traveling with you. So when you look at time, it's the watch that's traveling with you. When you look at length, it's the table or the ruler or whatever that's traveling with you. And when you look at mass, you're looking at the object that is going to increase in mass, but now you're not going to look at it as increasing in mass because you get it right there in front of you. And so that's the proper mass. And so what they're saying is that the proper mass is not the one that expands, that increases. The proper length is not the one that flattens out, that shortens, right, in the direction of travel, and so on. And so the question is, they're saying that the proper one doesn't change, meaning that there is no change, that it's only a measurement issue, and this measurement issue has to do with someone traveling at the speed of light in general, or close to the speed of light. And so we're talking about measurement. We're not talking about physics here. We're talking about the object did not change. Whether it travels at the speed of light, it did not flatten out. It did not gain more mass. It always remained the same. It's the measurement that they're talking about. They're saying, oh, we measured more mass. Oh, we measured that its length shrunk in the direction of travel. That's what they're telling you. But that's just a measurement. That's just, you can drink 4 or 5 beers and reach the same conclusion. If the object itself has not changed, if its frame of reference, it does not change at all, that's an objective criterion. The measurement, that's not an objective criterion, that's subjective. Because, you could be influenced by the way light shines on your eyes, how many drinks you had, it's got nothing to do with what the object itself did. The object itself did not change, they're telling you. In its frame of reference, the ruler remains 12 inches, didn't shrink at all, and it did not gain any weight. And so what have they discovered? Nothing. They're just talking about measurement, okay, of what they perceive. And here's a time dilation, okay, I've already proven, this is proof, evidence, okay, that Einstein's theory is wrong. Why? Because he says that if you take an atomic clock at the top of the Eiffel Tower there, it's going to take faster than the one at the close to the Earth, because according to him, the Earth, the gravity, whatever gravity is going to affect that clock in such a way that it's going to go slower. It's going to tick slower. But, if you do it with an hourglass, you arrive at the opposite conclusion. In fact, the clock on the bottom, the one closer to the center of the Earth, that's the one that's going to go faster because it's a gravitational clock. In fact, that's the best clock to test any theory that involves gravity and time. So here you have an hourglass, a sand clock, right? And it's ticking faster, closer to the center of the Earth than a clock that's far out on top of, the Eiffel Tower. And that destroys the principle of relativity, okay, which they take as a law of the universe or something, okay? And again, the other one is the Earth going around the sun, that's 1 year. I don't care how fast the twin went out there and came back. We don't care about that. We just want to know that when he comes back, hopefully the Earth went around the sun 20 times or 40 times or 100 times, but not 20 times for one guy and 50 for another. That doesn't happen. That only in relativity does that happen. Okay, so how do we get around all these things? How do we tackle these things? Well, we use my famous tool, the universal movie. Okay, here it is. What is this tool? Well, it's we look at the universe as single frames, as if God takes a snapshot frame by frame, okay, of every location that every atom in the universe, every object in the universe has with respect to all others. And for a given snapshot, when you take a snapshot, there's nothing moving in a snapshot. Well, that's going to be a frame. The next frame is the next snapshot. The next frame is the next snapshot, and so on down the line. So between these, there's very little motion, because as soon as everything moves 1/gazillionth of a billionth of a gazillionth of an inch, it's already a different frame, okay? So why do we do this? Well, we try to make sure that we understand the static concepts and separate them from the dynamic concepts. All dynamic concepts require at least 2 frames of the movie, okay? So static concepts, 1 frame. Dynamic concepts require at least 2 because you're talking about motion. Motion is what? 2 locations or more of an object, 2 frames of the universal movie. All the others, the yellow ones on the top, object, distance, location, and existence, they do not require 2 frames of the movie. Okay, so this is a useful tool to separate static from dynamic concepts. A lot of people have a lot of problems with this because they don't understand. It destroys their religion. That's what it really does. So they somehow tend to not understand whatever destroys their religion. That's all it's about. Okay, so where do we put some of these concepts from special relativity? Well, here you have weight, mass, and length. They are static concepts. Okay, we don't need more than 1 frame of the movie to conceptualize weight, mass, or length. What is mass? The number of atoms an object has. Okay, does it change from frame to frame? Yeah, maybe it does. We don't care because that's not what we're asking. We're saying, does mass in a single frame of the movie, does an object have the same number of atoms there? Or does it change in that single frame? And the answer is no. If a ball has 1 trillion atoms in that single frame, that's the mass of that object, 1 trillion atoms. So mass is a static concept. Similarly, length is the separation, from one surface to the other side of a surface of an object. Okay, we treat it as if it were made of a single piece. Table could be, for example. And so that's called the length of the table. We don't care how much it measures. It has no meaning in physics. Okay, we just care to know what the word length means. Okay, we don't roll the measuring tape from one edge to the other. In science, what we do is we define the word length. And weight, again, is the number of electromagnetic ropes, the individual, right? Electromagnetic ropes that bind any two objects. So again, the number of ropes is a given number in any frame of the movie. That's what weight is. You have weight for, it's location specific. You have weight only for a given location, okay, with respect to the Earth. You change your location, you have a different weight. Okay, so difference in weight, that's two frames. We're not talking about difference in weight, we're talking about weight. And that has to be a certain number of ropes at a given distance, distance being a static concept. Okay, where do we put all the others? This word increase, contraction, those are dynamic concepts. Volume, another dynamic concept, and speed. Okay, so all these are dynamic concepts that require more than one frame of the movie. So once we separate these, we can now begin to talk a little more intelligently about the conclusions reached by special relativity, especially with respect to weight, mass, length, and whether any of these change. Okay, and the question is, and the issue is no, they don't change, because again, they're even telling you that the proper length and the proper mass do not change, meaning the mass that is traveling with you, so to speak, you know, the one in your frame of reference. So if that doesn't change, then they haven't discovered anything. What they're saying is the guy far away in the other planet that's watching you, he measures, and he measures something different than what you're measuring there. Okay, we don't care. The real value is the one that you're traveling with. That's the important one, because that's what it is. That's objective. What the other guy measures, because he's traveling fast, or he didn't see it very well, he doesn't have the proper tools, or he drank too much, we don't care. What we care about is the objective. The proper length, the proper mass is the correct value. It's an objective value. So don't tell me that the thing increased in mass when it didn't. You're just saying that you measured it to have increased, meaning you measured the weight, because you don't measure mass. Mass is you count. You count the number of atoms of an object. Weight you measure. And what they're doing is measuring weight, how much an object that travels close to the speed of light presses down on the scale, and they call that mass. That's where their error is. It's not mass, they're talking about weight. Okay? And as far as length contraction, well, yeah, anything can contract, but again, they're saying that the proper length does not contract, and the proper time does not change either. The one that you have in your watch when you're traveling, right? That one stays with you. That doesn't change. What's changing is what the other guy is measuring with his clock about your motion. Who cares? That doesn't affect my watch. My watch is still, you know, measuring what it should be measuring. So if another person measures something different, you know, we don't care. And again, the way we settle these things is we come back to Earth and we say, how many times did the Earth go around the sun? And then you can divide that by days, by hours, by minutes, by seconds, and you'll know how many seconds really went, you know, around. You know, which clock is correct. The one that matches the number of seconds that the Earth had for 20 revolutions, that's the one that gets the cigar. That's how simple it is. So it's all very simple. In physics, it's all objective. There's no subjectivity. We don't use observers. We don't take measurements. We don't do calculations. We don't care about any of that in physics. Okay, in science. Math is a language, only it is, and that's why it has nothing to do with physics. You can never merge the language of physics with the science of physics. Never the twain shall meet. Okay, so what do we say in the end? We say mass, quantity of matter. That's what it is. Okay, in other words, proper mass. That's what we care about. Weight, number of independent ropes that between two objects, that bind two objects. Okay, independent or what we call effective ropes. Two objects are standing still at a given distance from each other. Snapshot, right? How many ropes are there interconnecting them? That's the mass. Okay, and length, continuous matter between, you know, two surfaces. Okay? So you have surface of the table. You treat it as an object made of a single piece. Table is not made of parts. We don't talk about mereology in physics. Okay, that's a religion known as mereology. What something is made out of. Okay, we don't care about that. We look at a table, we say it's made out of a single piece. We look at one edge to the other, and that's the length. Do we unroll the measuring tape to find out how long it is? No, we don't, because length here on Earth is the same as length, the definition of length, right? As in the land of the Klingons. Length is length is length is length. Always should be the same. Okay, I don't care if you're in the land of the Klingons, surface to surface. If they have a different measuring tape, different units, what should we do? Commit suicide and say, oh, but they don't have inches, and they don't have feet, and they don't have meters. What should I do now? They have the X's and the Y's. Yeah, that's why it doesn't matter. Length, we have to define, not measure. And then the other two notions there we don't care about because they don't belong to physics. Okay, they're stuff that belongs exclusively to mathematics. We don't have use for time in physics. We have no use for volume. Why? Because in science we have to explain a mechanism. That's what physics is about, explaining a physical mechanism. Time plays no role in an explanation, and volume doesn't either, as far as I can tell. I mean, I don't know. Maybe someone will find some way of putting volume in there. I doubt it. What is time? Relation between two motions. Okay, you have to have memory there to memorize the original points and then compare them against their ending points. And this fellow says, what if they're cheating on you? Irrelevant. We're talking about the definition, but he doesn't understand that. Okay, and then we have volume, displaced encapsulating medium. So if you have an encapsulating medium such as water, right, or air, and you're going to put the fish or the bird in the air or the fish in the water, how much water does it displace? That's called volume. Okay, so it's a dynamic concept. Okay? Again, we have no use for volume in science. Okay, and with that, I guess we clean our nose holes with all of relativity, special relativity, right? It has no validity in science, and it has nothing to do with physics at all. What these people are talking about is measuring and subjectivity. That's what they're talking about. Physics is objective. There are no observers in physics, no measurement, no equations. We don't use words such as time. It's a four-letter word, okay? Literally, okay? We don't use those words. We have no use for time in physics. And mass, number of atoms, I don't know if that has any validity in physics. Maybe you could, have some use for it. The only way I use it is to say that the atom, the hydrogen atom, is the unit of mass. Okay, that's one way that I use it. The more hydrogen atoms, the bigger the element is. Uranium has 92 hydrogen atoms, essentially. So in that sense, I use mass. Weight, the only way I use it is just to explain that weight is a static concept. It's location specific. You move an inch farther away from the earth or closer to the earth, you have a different weight. So weight is location specific. Location is a static concept. What are we talking about? We're talking about the number of ropes that interconnect every atom of one object to every atom of the other object. That's essentially the main point. Obviously, each one of the objects is also bound to every other atom in the universe by electromagnetic ropes as well, and those intervene as well in this tug of war. Okay, so all that's got to be factored in to the notion of weight. Okay, and that's different than the acceleration of gravity, by the way. Acceleration of gravity when you have many weights. Wait. And as you get closer, the ropes fan out, and you have more independent ropes, more effective ropes, and therefore weight changes as you approach the Earth. That acceleration of gravity is many weights, many measurements of weights, okay?